Quick logistical items, especially for technical difficulties. If you have any audio issues, recommend trying to connect through your phone. If that doesn't work, there's the Zoom Help Center webpage. Do a quick Google search for that. Questions, comments, concerns can be submitted through the chat box. As an overview of today's webinar's agenda, we'll first give a really brief introduction to the prize and some of the people who are particular to this webinar. Then we'll dive into explaining a bit more in a version 3.0 way, if you will, regarding distributed embedded energy conversion technologies, DEEC-Tec. And then we'll segue into direct generation presentation given by Wave Energy Scotland, followed by a question and answer session, and then a quick wrap up of today's webinar. So right now, as I'm sure most are aware, we're in phase 3 of the InDEEP competition. More information can be found at the website indicated at the bottom right-hand corner, herox.com/InDEEP. In today's webinar, we have myself, Blake Bourne, who hails from the National Renewable Energy Laboratory, along with Joachim Weber. And then from the Wave Energy Scotland side of things, we have Ian Collins and Jonathan Hodges. Diving into distributed energy conversion technologies, I'll turn the mic over to Joachim.
Hello, everybody. Hi, thank you, Blake. Yeah, this next 3 slides are a little bit to set the scene on where this domain came from and what motivation is, and to make it easy to understand the approach. So we have an analogy here out of an entirely different domain, which is solar power. So on the left-hand side, you see the version of solar power which has concentrated energy conversion. So thermal solar power. So what we have is that the aggregation of the power is done in the original energy field on the solar side with the mirrors, concentrating this energy into a power conversion chain and then dealing with this very concentrated power conversion into, thermodynamics going into a turbo machine, into a generator. So conventional. And thanks. And so this is concentrated energy conversion. And on the other hand, you see photovoltaics. What does that mean, actually, what is being done here? So that we have directly in the field, we have small modules that are distributed in the original source field of the energy that we're tapping into. And then the energy is converted into electricity, and the aggregation happens on the electricity side. So that's kind of an analogy to say what is concentrated energy conversion, what is distributed energy conversion in a different domain. And of course, many advantages or many properties come along with that. For example, scaling is now by numbers. Redundancy is embedded. Surely we still have to bring things together on the aggregation, and there might be single points of failure, but it's an entirely different approach. And for wave energy, that would mean that the wave energy absorption, so some kind of a hydrodynamic, hydromechanical conversion and interaction is used directly to create electricity, which would mean, if there's a direct interaction, the most comprehensible or obvious way of doing that is that there's some kind of a dynamics going on, some kind of a motion. And if there's a distributed response of motion on a structure, well, that would imply that the structure is deformable, that it can change its shape because it will respond in different locations on the surface in different ways. That means it deforms. Or that these motions, these local motions, they may not add up to replicate the motion of a solid body. Okay, so I think that's about this slide. Next slide, please. Okay, so what's important to realize is that the absolutely significant portion, 90x% of the research that happened in the last, 2.5, 3 decades of wave energy since the 70s has been dealing in some sort with concentrated energy conversion. So how do we bring the hydrodynamics together into a joint, a linear bearing, relative or absolute? How do we accumulate water flow in overtopping devices? How do we accumulate airflow in oscillating water columns to have it in a concentrated way to deal with that, and then apply power conversion mechanisms that we are familiar with, where we then maybe have challenges like bringing the velocities up to what a generator would like to see, but they're all in some way concentrated. Even, you know, lift-wack devices, lift-driven devices, a very different species, would try and get the hydrodynamics onto a shaft. Yeah, and things like hinged barges and heaving buoys and all of that, you know, they are perfectly fitting that scheme. And as I mentioned, concentrating flows in overtopping or oscillating water columns. So I'm not saying in any way that we've exhausted that innovation space, but there have been and still are big efforts and big research projects and a lot of the industry that is servicing this research space. So on the other hand, let's look at what we have in terms of distributed energy conversion. So we have some projects. Obviously, this slide would probably need a bit of updating in terms of the research that has been done so far. So in the old days, or in the early days, I should say, yeah, we had the clam. So there were deformation systems definitely there. And I'm kind of mixing up, but I want to make the difference clear between deformation, which doesn't mean distributed energy conversion, it just means deformation. So not a rigid body degree of freedom, but a deformation body degree of freedom, which does not mean distributed, but it might in some modification lend itself. So the clam had that to some degree. It had individual modules that reacted differently to what you could regard as a deformation. So that's an early Scottish device. So was the clam actually? Yeah, I think it was Scottish, or was it Manchester? I forget, but the clam. Then Anaconda, that is really a distributed, sorry, that is really a deforming system, but it's not distributed. There's internal flow still accumulated. The Flexconda is a bit different. So there are some activities. Polyvac European project, we've had some European projects looking at wave energy. Scotland has done a lot of work in this domain. We've done some work started with FlexWac and then was changed into DEEC-Tec. And of course, absolutely important to mention, SBM has done a huge amount of work and the most advanced work in trying to get this domain to fruition. So all in short, there is a lot of unexplored space for innovation, for R&D, and that means challenges and opportunities. Thank you. Next slide, please. Okay, so this is, we just looked a little bit into the timeline, a little bit back, what has been done in the past, you know, talking about things like the clam. So this is a simple timeline to just put together on where this project for us came from. So we've had a project that used to be called Structured Innovation, and now it's called WaveSpar for quite some time. And it's you know, in its most simple way, it's supposed to be a machinery that's going to spit out tools and spit out concepts for technology innovation and development. One of the tools is the TPL, and the other ones are concepts that have been generated in these projects. Many of them were not published, but there's quite an amount of ideas and concepts came out of it. And when these concepts and ideas are worthy enough to deliver merit for their own project, so they're not being carried in WaveSpark anymore, then new projects were born. And out of a lab call we had some years ago, the FlexWac project, and then when that transitioned to a more continuous project, that led to DEEC-Tec. Do you see this here? So, and in the same way as these projects came out of it, the prize came out of it. So the InDEEP prize that we're talking about here. There's also a previous prize. It's somewhere there on a smaller level. The Wave Energy Prize on the top left. We didn't put a new bubble in for it, but that's also where this project serviced a prize. And in the same way that this project serviced the prize, now InDEEP is servicing, DEEC-Tec is servicing the InDEEP prize. Okay, I think that's it from me. So I'll hand over back, or is there another one from me? Okay, Thanks.
Thank you so much, Joachim. So now getting into what DEEC-Tec is from the perspective of the prize, it can be summarized through 3 hierarchy levels. Looking at this particular wave energy converter that's based on DEEC-Tec, we're going to go ahead and call it a bottom fixed surging FlexWEC. I want to really point out to those who are listening that this is just a reference of an ocean wave energy converter that is based upon DEEC-Tec, and it's really only serving the purpose of trying to illustrate very concisely what the hierarchy levels of DEEC-Tec is, what DEEC-Tec is. So please don't think that a bottom fixed surging FlexWEC is the only rendition or implementation of DEEC-Tec into a wave energy converter. As what's trying to be conveyed on this slide, there could be any number of types of wave energy converters based on DEEC-Tec, ranging from a bulging line absorber, not too unlike SBM S3's device, for those of you who are familiar with it, or some sort of, in the bottom row there, distending point absorber, something that can contort and distend. So many different ways that you can leverage DEEC-Tec into an ocean wave energy converter. For now, for the sake of this webinar, I'm only going to leverage the bottom fixed surging FlexWEC to convey the hierarchies of DEEC-Tec. At the very highest level of the DEEC-Tec hierarchy, we have a complete structure, a complete energy converting structure. And in this case, the complete structure is an ocean wave energy converter, the bottom fixed surging FlexWEC. When we look inside what's being made up to be this wave energy converter, we see internally that it's made up of 2 metamaterials in this particular case, which represents hierarchy level 2 of the world of DEEC-Tec. We have a DEEC-Tec metamaterial that's a lattice, that's trying to be indicated on the far left, and then it also is made up of a DEEC-Tec metamaterial that's a column, that's shown in the bottom left. So this converter is made from 2 varieties of DEEC-Tec metamaterials. And what I want to point out is that not only is this converter made out of 2 different types of DEEC-Tec metamaterials, but the DEEC-Tec metamaterials themselves are made up of different individual distributed embedded energy converters, which is the first hierarchy level of DEEC-Tec. Now, these individual distributed embedded energy converters are just pictorial representations that's really trying to convey that these individual energy converters, these individual energy transducers can come in any shape, form, or color, and that they can be interchanged, mixed together to form any number of different types of DEEC-Tec metamaterials, like what you see on the left of this screen. In summary, we have these individual distributed embedded energy converters. I also call them just energy transducers, making up DEEC-Tec metamaterials that make up an ocean wave energy converter. And when an ocean wave, in the case of this bottom fixed surging FlexWEC, is subjected to those waves, will twist and bend. And by way of dampening that motion, because the structure itself is made of these energy transducers, ocean wave energy is converted into, for example, electricity. Now, this begs the question, what are the various types of energy transducers that can be implemented? What are the various types of DEEC-Tec metamaterials that can be implemented? I gave 2 examples of DEEC-Tec metamaterials using pictorial representations of the individual DEECs. Namely, I represented a lattice and a column, but it could really be anything. It could be woven fabrics or something of that. And this presents a really great opportunity to leverage pre-existing domains of technology and research, such as polymer research or soft robotics research, to really sort of flesh out and suss out what can be developed in terms of individual DEECs, the energy transducers, and DEEC-Tec metamaterials. This is irrespective of the wave energy converter itself for the sake of this particular slide. So what this means is we can leverage these pre-existing technologies to de-risk the domain of DEEC-Tec and really try to make sense of what's currently available and what may not be feasible. And this begs the question in terms of the contestants of the InDEEP competition, is your technology going to solve some of these questions in terms of what an individual DEEC can be or what a DEEC-Tec metamaterial could be? And that's pretty exciting. If there had to be one thing I wish all would take away from this presentation today, it would be the message that's conveyed on this slide here, which is DEEC-Tec is the creation of larger energy converting structures by distributing, embedding, and interconnecting many smaller, or relatively smaller, energy converter transducers together. Jakob mentioned earlier that a motivation of DEEC-Tec was that there was a pretty big domain and gap in research for those ocean wave energy converters based on distributed embedded energy converters, especially relative to the classical notions of those wave energy converters based on large rigid bodies. But here's some additional motivations of why one should take interest in DEEC-Tec. As Jakob mentioned, there's a lack of concentration of forces into a singular prime mover. In other words, there's a lack of concentration of energy converting forces or moments into like a giant generator or hydraulic piston, right, is instead distributed throughout the structure. DEEC-Tec also avails the inherent ability to be redundant. If one of the small energy transducers fails, probably okay. You have 1,000, tens of thousands more of those energy converters still operational. By virtue of the fact of creating a wave energy converter with multi-bodies with multiple individual distributed embedded energy converters, you have multiple degrees of freedom, multiple eigenmodes. You immediately are accessing different wave periods of the ocean wave energy resource that you wouldn't be able to access. So you have a much better ability to capture across different seasons of ocean waves, different types of ocean waves than what would otherwise be possible. And then the fourth sort of additional motivation I want to share with those listening that I think is really unique and pretty powerful of DEEC-Tec is that it inherently expands the design space of possibilities of how we think and innovate towards marine energy conversion and usage. Ideas that heretofore we have not really fully appreciated or even known existed. And so DEEC-Tec is a pretty powerful, what would you call it, domain or just step change in how we think about marine energy, really opening up and enabling a more diverse view of the conversion process. Also, because this is the version 3.0 of the DEEC-Tec webinar, I want to mention that DEEC-Tec is not just applicable to marine renewable energy, but could be applied in other applications, from energy storage to human locomotion. And this slide also is a summary of the 3 hierarchy levels, indicating that you have individual decks that make metamaterials that make some structure for some application, even beyond marine renewable energy. A new addition also to the DEEC-Tec webinar 3.0 is looking at possible metrics for success. So in our own research here at NREL, what we've been able to sort of suss out is that a possible metric for DEEC-Tec technologies or innovations is we're looking at longevity, likely power density per wave period, ease of manufacture, controllability, in other words, ability to actuate and sense. It's sustainability. How does it interact with the marine environment? Is it using rare earth materials or strategic materials? And also, how easy is it to integrate these individual decks together to form metamaterials, to form structures? And that's a unique feature of, or a pretty unique feature of DEEC-Tec. Coming full circle, I want to mention that yes, there's been a lot of research and money spent into the concentrated energy conversion domain of marine energy, and rightfully so, and it still should be researched and developed. But there is this glaring gap in the underexplored territory of distributed energy conversion for marine energy converter devices. So this is a fantastic opportunity, DEEC-Tec and InDEEP, to further explore that area. And now I will turn the time over to Wave Energy Scotland to talk a little bit about direct generation, which is, I would argue, a very analogous form to DEEC-Tec, but probably with more greater focus in those energy transducers based on variable capacitance. But without further ado, I will let them introduce a little bit more about their research.
Thank you, Blake. Can you hear me okay?
Yes.
Great. Good afternoon, good morning, everybody. My name is Jonathan Hodges. I'm Innovation and Strategy Manager at Wave Energy Scotland, and Ian Collins is on the call with me as well. He is our Innovation Engineer. Thank you very much for the invitation to take part here. I know that we've got some people on the call from the UK and many from the States and elsewhere as well. So really nice to get the opportunity to talk to you. I've just got a few slides of introduction here to explain to you why Wave Energy Scotland are speaking to you this afternoon, basically. So Blake, if you go to the next slide, please. Just as an introduction to Wave Energy Scotland itself, we are a public funding organisation based in Scotland. We were established in 2014 by the Scottish Government, and we are funded by the Scottish Government with the target of developing cost competitive wave energy technology. And we've been doing that now for nearly 10 years. The programme has committed over £50 million, 130 odd projects. Those projects have been based in countries all over the world, with all of the physical testing activity happening in Scotland. And that programme has been based on a stage-gated mechanism. So it's basically a competitive programme over 3 stages. And that programme has been based around 5 competitive programmes in what were deemed to be the key 5 areas of technology: power takeoffs, wave devices, control systems, materials, and quick connection and mooring systems. So on the next slide, please, Blake. Here's an example of the types of technologies that have emerged from the programme. These are the headline devices that have come out of the novel wave energy converter call. One from Motion Energy, which is a hinged barge, and one from AWS Ocean Energy, which is a submerged pressure differential device. Those have gone all the way from concepts through to part scale, large scale proof of concept testing in the waters of the European Marine Energy Centre in Orkney in Scotland. And those have been supported by enabling technologies from the other calls. So power takeoffs, quick connection systems have all been merged into those technologies, or will be in the future. And you can see on the right-hand side some of our current activities, which is all about trying to create a pathway to commercialization for those technologies. And one of those pathways that we're working on is co-location with floating wind in particular, and the opportunity for clustering numerous devices on a supporting platform. So that gives you an idea of the headline, all the way from concept development through to large-scale proof of concept testing. But on the next slide, please, Blake, you can see the format of that over the years, starting with power takeoffs, and you can see that each call is split into 3 stages. And a really important part of our program is those stage gates, where all of the projects compete against each other to go through to the next stage, an increased amount of funding, very specific requirements in terms of activities that are carried out in each stage, and in terms of the data, the metrics, the evaluation that comes out of each stage gate and out of each project. So all of those stage gated programs have been run by our team, and we're currently running a European version called Europe Wave, which is another pre-commercial procurement program developing large-scale devices. One more click, please, Blake. What we've found through that program is that you can see we've had projects which have either been based on dielectric elastomer generators or flexible technologies throughout our program. And what we found was that there was definitely attractive characteristics out of each of those projects, but due to the relative maturity of those technologies compared to the other steel-based and electromagnetic generator-based technologies, none of those, with the exception of one, got through to stage 3. So we found that we had these technologies which were clearly attractive, clearly had benefits compared to some of the more conventional technologies, but weren't comparable in terms of maturity. And the mechanism of our program meant that the majority of those fell out of the program, either in stage 1 or stage 2. So our part of the team set about trying to understand how we could investigate those types of technologies further, and how we could support those towards the point where they might achieve that competitiveness and that compatibility with the larger scale programs. Next one, please, Blake. So we started to look into that partly through internal research, partly by funding what we call landscaping projects, where we had consultancies look at all the different opportunities for these types of technologies, and partly through academic routes. So we co-funded and co-supervised a PhD by a guy called Paul Kerr at Edinburgh University. And he looked, first of all, in his first year, into radical innovation in general and what impact it can have on on cost of energy, on the trajectory towards lower cost of energy, and also the investment required to support the development of that technology. And what we found is that introducing radical innovation can bring about step changes in levelized cost of energy. It can allow you to jump down the graph to the right to access higher learning rates, and it can vastly reduce the amount of public funding needed to support the achievement of levelized cost of energy targets. And we could see that these types of technologies, these radical innovations, are a way for us to access longer term cost reduction beyond that available with more conventional technologies. So that gave us some justification to look more deeply into this type of technology in particular. Next slide, please, Blake. So what do we do? I mentioned a couple of these already. We had a consultancy called Fraser Nash do a landscaping study onto what we called alternative generation. That was probably about 6 or 7 years ago now, and we asked them to look at all of the different types of technologies for converting movement or force into electricity through alternative means away from electromagnetic generators. And they then down selected what they thought were the most promising, most likely to be achieved in a reasonable timescales, and that gave us some guidance on where to look next. We had an internal project called Project Seaweed, which we took a completely different approach to this and said, what if X were possible? Would that give us an attractive solution? So it allowed us to completely step away from the analytical side of things to say, what is the capability of this technology? And just to say, what if this were possible? What direction would that take us? And that gave some interesting steers as well. I just spoke about Paul Kerr's PhD. All of this led us to the point where we started to down select. And this is the really interesting bit about the collaboration between Wave Energy Scotland and you in the States. We have down selected our program to focus on dielectric elastomer generators, DEGs, and dielectric fluid generators, DFGs. And as Blake said, those are technologies which are based around the physical characteristics of capacitance change, variable capacitance. So that's where we have started to differ from the US program. We've down selected much more. Next slide, please, Blake. And that gets us onto collaboration. Why are we on this call, and what have we been doing with the States, with the United States over the last 10 years at least? And we have had a really, really fruitful collaboration between us with the national labs and with the Department of Energy on varied topics. A central thread of it has been evaluation techniques, which is very important globally, of how we direct our public funding globally towards the most promising technologies and the most promising innovations. We've looked beyond that towards technology development guidance of how you develop people and technologies through the pathways in the most effective ways. Joachim mentioned the word structured innovation, the title of one of the programs that you've had going in there for many years. And we took a similar but slightly different approach to structuring the innovation process. And we had some really, really valuable exchanges of comparing and contrasting those approaches. And then we've started to focus together into radical innovation and power conversion technologies. And the benefits of all of this collaboration, these knowledge exchanges, has been our ability to cover a wider scope between us than we could separately, and to be able to exchange knowledge on the benefits, the directions, the attractive areas, and what research projects we're supporting. To be able to compare and contrast different approaches. We've always had a slightly different approach in a similar area, and that's been really valuable. And it's created mutual benefit through that sharing. And overall, to be able to help guide each other to avoid repetition of the same funding activities. And it's all intended to avoid multiple uses of public funding for the same thing. So that brings us to be able to present to you today. As Blake said, and as I've explained, we now have this program called Direct Generation, in which we are trying to push forward this area of technology with a slightly narrower scope. And I'm going to pass on to my colleague Yayan, who's going to talk about what our program looks like and our strategy and the types of projects that we're supporting at the moment. Thank you.
Thank you, Jonathan. Jonathan just sort of gave us an overview now of how we got to this point where we wanted to investigate direct generation. So I'm going to talk about how we are investigating it. And it's, I guess you could say we sort of kick-started this whole program with a design competition. And that's that green box there. And we've used that design competition then as a way of sort of informing our own understanding, demonstrating the benefits of these technologies, and crucially identifying the R&D requirements which feed into this sort of larger cross-sector enabling R&D program. You can see the sort of boxes there. So if you could just click through a few animations, please, Blake. And yeah, so and one more. There we go. Thank you. So round one of that competition completed back in February. I'll talk about like an overview of how that all worked in a few slides time, but just the sort of main takeaway from this slide is, so on the right, we've got the sort of developers identifying all those R&D requirements. On the top left, then we've got these researchers doing the fundamental research from materials all the way through to modular generators. So there's a nice exchange of flow of information from developer to researcher. So next slide, please. So round one then, some of the outcomes of that competition, which finished earlier this year in February. So as I say, we've developed that community of expertise now. We've got a much better understanding of wave energy, elastomers, and electrostatic energy generation, and we've brought together sort of people who may not otherwise be talking to one another all together in one large cohort, working towards a shared goal of direct generation. We have a much clearer understanding of what doing that design process has given us then some sort of hard numbers to back up certain design claims and choices, which has been very useful. And doing that process has also given us, as I said in the previous slide, the enabling R&D, which we need to do to get us to that point of, development exploitation. So we've sort of developed a research agenda which sort of lists all that R&D, which I'll talk about near the end. And then finally on this slide, there's the design and evaluation process. So going about doing the design of a wave energy converter sort of makes you realize what you should be prioritizing in terms of design, especially at this low TRL. So there's some unique components to direct generation where we want to try and incentivize at this low TRL and make sure developers are making the right decisions from the get-go. Next slide, please. Obviously, I think it's yeah, that's good. Yeah, so to conclude then, so direct generation, based on our first round of the competition, was given us sort of confidence that there's a lot of potential for wave energy, but we're not at that stage now where we can realistically say that we can take it to a larger scale development. So we need further enabling R&D to get to a point where we've got increased level of confidence. So if you go to the next slide, please, Blake. And that sort of brings me on to a timeline. So as I said, we had round one of these concept design projects finish back in February of this year. And that's fed information then into this larger cross-sector R&D program. Alongside this round one, there's been a sort of co-funded Wave Energy Scotland program, which is funding postdocs and to do the research in the relevant areas. And if you could just click a few animations through, and we want to be getting through to that point of we want to get through to that point of large-scale developments, as you can see on the right there, but we're not sure when we're ready for that. So that's where we've got a second round now of this concept design project in order to sort of bridge that gap, further elaborate our knowledge, and keep on identifying that doing those identifying R&D requirements in order for people to do the enabling R&D. Yeah, next slide, please. So this then is like a sort of flow chart then of the whole sort of project, all the people involved. So I've been talking about round one. So in round one, 14-week period starting from October to February this year, and each team was awarded £50,000 each. And there were 5 teams involved in that, with a range of sort of technology studied. We had both dielectric elastomer generators and dielectric fluid generators. So there's a good sort of almost not far off a 50-50 split in what's been sort of analysed from each team. And once that finished, then we invited the project leads from that round 1 to apply for a second round, and 2 successful applicants of that were 4C Engineering and TTI Marine Renewables. And that's essentially a much higher budget, longer duration sort of project with 200,000 each, and we've got a nice 50-50 split of one looking at a dielectric elastomer generator and the other looking at a dielectric fluid generator. And that top right then is just showing the R&D projects which are sort of happening alongside this round 2, and there's that nice knowledge exchange between the 2 groups. So we're looking at, again, DFGs, DEGs, and electromechanical fatigue. I'll talk a bit more about it on the next slide. And that yellow box then is just a sort of highlighting the fact that although some teams may have been eliminated in the first round, there's still sort of opportunities for them to play a sort of a supporting role in an R&D project or a subcontract role in a round 2 team project. Next slide, please, Blake. Okay, so this is just a summary then of the R&D projects. So we've got a good range here from DEG, DFG, and the fatigue side of things. So University of Manchester is looking at developing a flexible electrode solution for dielectric elastomer generators. So I'm not sure how familiar you may be, but one of the main challenges of DEGs is the fact that you've got a sort of mismatch of sort of straining and non-straining electrode materials. But with the Manchester project, they're looking at sort of overcoming some of those problems by doing a more homogeneous sort of conductive elastomer nanocomposite, where there's less mismatch between the materials, and the electrode is essentially stretchable. So that started back in June. Another one which started around the same time was the University of Oxford project. And that's looking at DFGs, but using origami-inspired structures to sort of come up with a sort of cellular design. And they're doing sort of mock-up designs, sort of illustrating those deformation modes of different unit cells and doing some sort of preliminary modeling work then to understand that capacitance change, which that will then inform and iterate the design. Later this month, we have a longer duration PhD project starting, which will investigate the electromechanical fatigue of both DEG and DFG units in a more agnostic sense. So they'll be doing a comprehensive experimental campaign, starting off with fatigue experiments and material characterization under sort of biaxial straining conditions, so a dual actuator setup, and they'll eventually lead to sort of coming up with their own sort of designs based on the findings in experimental study. Next slide, please, Blake. So some of the outputs from Wes's point of view have been, during the first rounds, we sort of generated so much R&D requirements, and we sort of needed to group it all together into sort of 4 different themes. And we came up with material selection, module design, manufacture and integration process development, and wave energy architecture development. So those 4 themes taking place from that centimeter scale all the way through to meter scale. And within each of those themes, then there's a series of subtasks which need to be fulfilled in order to get to that point where we can realistically exploit and develop these technologies. So we're sort of in the stage at the moment where we're sort of drafting up the document, which we'd like to share with the wider community. And one thing which is quite important to emphasize on this slide then is the overlap in R&D then with other sectors. So we don't really want to avoid duplicating research in some areas where, say, software robotics might have similar aspirations or requirements. So it's also being mindful of the fact that other sectors are trying to answer a lot of these research questions as well. So keeping that in the back of mind is very important too. Next slide, please. And another thing which we sort of generated through this process as well is the evaluation and guidance. So doing that first round, we came to the conclusion, yes, we can use these established frameworks from IEA, OES, and TPL, which are very good. But right now, we've such a low TRL. We want something which is really easy to quantify very quickly. So that's where that brings us on to sort of more of a streamlined approach to evaluation. And we want to incentivize developers to realize a lot of unique benefits to direct generation over conventional architectures. So direct generation offers new design possibilities such as flexibility, foldability, modularity, and so on. So it's about trying to get those metrics to fully sort of give bonus points to designs which focus on realizing those benefits. And on the left, you can see the sort of 5 areas of sort of evaluation. So going down from power density to sustainability. It's also really important to so balance different aspects of design. So if you just click through a couple, you should come up. Yeah. So this is where I sort of talk about combining metrics is quite a valuable tool at this early stage. So a good example is sort of priorities in the design, which has a very good power density at the consequence of longevity. So having a metric such as through life energy density sort of automatically finds a good compromise between the two. So it's being mindful of the fact that we can sort of try and balance these different metrics across different aspects of design and make sure we're not prioritizing one more or too much over another. And there's other sort of examples from like embodied carbon costs and cost of energy metrics, which also you can sort of combine with others. So I think that's sort of almost a similar end to the sort of Blake's presentation, and that's pretty much it from me. I'd be happy to answer any questions in the Q&A session. Thanks a lot.
Thank you, Yain. Okay, moving and diving into questions and answers. I see one hand up from Peter McDonald.
Yeah, apologies. That was an accidental request to hand up. But given I've got the mic, I will just say thanks to both for the presentations. It was very useful and particularly good to see the kind of collaboration mindset with kind of some areas of overlap, but looking to kind of make sure that public money has been used effectively to explore different bits and pieces. So it's more of a commendation to both organisations for the positive programs and for the updates. So thanks for that. But no, I didn't actually have a question. So apologies there.
Fair enough. Luckily, I think Tony Noser, did you have your hand up? Please feel free to ask away.
Oh, no, I was just agreeing with the last fella and saying great presentation. That was very well laid out.
Thank you very much.
We do have a question in the Q&A. Can you elaborate on fluid decks? Yeah, anybody?
I can, and then maybe I'll toss it over to Yain. So dielectric fluidic generators / actuators are those energy transducers based on variable capacitance like DEGs, but whose dielectric is predominantly a fluid, typically a transformer fluid, even vegetable oil. A commercial representation of that would be called Hazel's, self-healing actuator. I don't remember what the acronym stands for, but essentially you have 2 electrodes on either side, and those electrodes are on a bag. And then within that bag is a dielectric fluid, vegetable oil. And it works predominantly the same way as a dielectric elastomer generator. If you compress the bag and then you pre-charge the electrodes, and then the bag is able to release due to that fluidic pressure, then you boost the voltage generating electricity. And please feel free to augment or correct anything I've said.
I think that's a really good explanation. Yeah, so it's essentially what Blake said. It's sort of analogous to a DEG, but you're replacing an elastomer with a fluid component. You're bringing those electrodes closer together, but instead of straining the elastomer, you're moving a fluid from one cell to another. I think that's all I have to really add on it. But there's a couple of good research papers if you want to sort of learn more about it. If you just type into Google Scholar, it'll come up.
Oh, thank you, Paul, for the question. Let's see. Did the panelists? I don't see any more questions and answers. Okay, what are some challenges still facing DEGs and DFGs? Charge density. Again, I think I'll speak first and then pass it over to likely Yain. One of the challenges I've noticed with dielectric fluidic generators is longevity. I think that's a open research question. And then in terms of, let's see, dielectric elastomer generators, I think a big open research question is how to innovate a electrode that is both highly efficient in conduction and also stretchable. So most DEGs leverage a form of carbon dust grease. Yes, conductive, efficient, no. So that's a very open research question. Anything to add there, Yain?
Yeah, well, you've basically took my two answers I had popped in my head. So the first one I was going to say was also fatigue and the sort of flexible or stretchable electrode, but some other stuff, includes sort of synthesizing a material which has the optimum electrical properties. It's quite obvious, but we're still sort of doing a lot of research to try and get to that point where we can get a material which has good electrical properties whilst also balancing that with the fatigue and the electromechanical fatigue. There's also two components to that. There's a sort of physical sort of crack growth fatigue, and there's also the electrical side of fatigue as well. So I think a lot of research in that area is sort of required to get to that point where we're more confident in these materials.
Yes, awesome. And then what I was about to say before the chat question is I wanted to turn it over to any of the panelists. I'm thinking maybe Bill, Joachim, Jonathan, anything to add or express?
Well, maybe I can just echo more or less the gratitude and the great pleasure to have this international collaboration. Sometimes not that easy to do because we can't have money flowing across borders to some degree. So it's very good that we have independent, well-connected, well-communicated activities and creating synergy. It's a real pleasure. So thank you to Wave Energy Scotland. And
Yes.
yeah, I mean, looking back over the years, we had this timesheet on there when we had the lab call, and when I think on how long this whole idea, not just carried by us, by many others, has been around. Yeah, it remains to be a domain of great opportunity and great challenge. And this may also lead to the question, which are the particular advantages of these types of technologies? And out of that, what are they good at doing? And what are the markets that are good at asking for that? So, I'm just saying, will this be power to the grid? Will this be ocean observation? Will this be micro sensors floating in the ocean? I don't know. So I think it calls for having an open mind towards finding also applications that really calls for where the advantages of these archetypes are seen and can flourish. That's my
Thank you.
Here. I'll hand it on.
Thank you.
Yeah,
Joachim.
Thanks, Joachim. That's exactly right. And you mentioned they're open-minded to applications, and I think every time we do webinars like this across borders, there are links perhaps created between participants who are maybe competitors, maybe collaborators in future funding applications into other funders, and particularly looking at applications into public funders or private investors in other applications, because Blake mentioned that there are lots of different applications, whether it be generators, actuators, sensors for this type of technology. And there are lots of different industries with uses for those types of technologies, and the enabling R&D and the enabling technologies crosses between those applications with it and between those industries. So if we can work together to create a bigger and bigger cohort of people active in this field, then you guys can go and find applications in other industries and funding programs and overlaps in enabling R&D, and it just spreads the effort and it spreads that that benefit of the work we're doing here and vice versa. So that would be almost a request to everyone to look for those opportunities to collaborate and look for opportunities in other applications.
Absolutely. I just quickly wanted to point out, Paul, any thoughts on self-healing that have been achieved so far? I know the company Artemis Robotics, for their dielectric fluidic generator, has promoted a bag that sort of self heals by the polymer itself that the bag's made out of, and or the dielectric helps seal the bag after it's been, say, punctured through dielectric breakdown. Definitely a leading area of research, just like stretchable electrodes and developing longevity of DEGs and DFGs. Anyways, Paul, those are my thoughts. If anyone else wants to chime in on that question.
Yeah, I'll just say, you know, one of the unique benefits of dielectric fluid generators is the potential for that sort of continuous self-healing capability, because it's a fluid as opposed to a solid. So there's a couple of options there in terms of that design, and generally I've read several papers on sort of self-healing. There's lots of different approaches in the literature on how people are going about it, with sort of crack bridging and sort of adding additives to the material. So yeah, it's a really sort of interesting field of neat research right now, but it's still quite early days to sort of realistically say it's definitely going to be a viable solution for this sort of technology.
Yes, excellent.
Maybe one more thought, particularly when it seems like self-healing come up. Well, how do I get that bow to come together? You know, that's a general comment. Often in engineering, we try and do things that nature has done so much more beautiful and complete. And the self-healing, you know, look at yourself. I just had a surgery last week. I'm self-healing. So nature does these things beautifully. And maybe this domain, because we're looking at systems that are not kind of rugged mechanical engineering solutions where you come back to joints and hinges and bearings and stuff. So this is made closer to nature in a way. And maybe what would be good if we really target to go out and do some biomimicry, you know, to look at solutions, how they are in nature, where, you know, we might be learning something from it, because this is closer to other biomimicry explorations that we've already solved very well in kind of rugged mechanical engineering or stuff like that. Just a thought came up, wasn't really meant for this webinar, but might be triggering some ideas for people who are listening.
Thanks, Jakob. Anything else from the attendees or the panelists? I'm wondering, I hate to do this, but Bill, did you want to do any shout outs for WPTO and sort of their vested interest in DEEC-Tec and the prize?
Yeah, thanks, Blake. Just generally, I really appreciate, well, Blake, for you putting this on and for all the panelists participating. And I'm just repeating what was said. It's great that, you know, we are doing this, Scotland is doing, we're independently coming to the conclusion that this is a promise, you know, a great area for research, potentially interesting. I guess for the Water Power Office, we have lots of invested in rigid body forms of wave energy converters, and so that there appears to be lots of opportunity in these non-rigid things, and these distributed embedded energy converter ways of doing business is very interesting to us, and so we're looking forward to finding ways to continue this research. I hope the participants that are listening when you see open topic, we generally write our solicitations quite broadly. So when you see these things that are open topic, and if you have one of these DEEC-Tec solutions, I hope you guys consider putting a concept paper and full application. But I guess like my big picture thought is this prize has been super exciting. The things that we've seen, the proposals we've had, the interactions that we've had, and we're really looking forward to a great phase 3. And thanks everyone for participating.
Thanks, Bill. Then without further ado, let me go ahead and reshare my screen to go over the last slides, just wrapping things up. So please always feel free to provide us feedback on this webinar or any webinar that we give. And likewise, we're encouraging feedback on your submissions. We have some great mentorship, whether it be through people from NREL or Wave Energy Scotland even. We have Wave Venture and Ramble in particular. And then there's going to be additional resources linked in Appendix C of the rules document. The rules document can be located here at this URL. So if you want to do a more in-depth look at the prize overall and where these topics will be applied, that rules document is a great resource. Well, attendees, panelists, I have nothing more to add, and I'm happy to adjourn now.